Alright, so today we're going to be going over combinations and permutations. So combinations and permutations, they refer to the ways in which a group of objects can be selected from a greater group. So like if you have a set A, B, C, D, E, and you want to choose two arbitrary letters from there, how would you do that? You would calculate those using combinations and permutations. And the difference between the two is that combinations, the order doesn't matter when you're dealing with them. So if again I have A, B, C, D, E, and I wanted to choose two of them, then the number of ways to do that without ordering would just be AB, AC, AD, AE, and then we have BC, BD, BE, CD, CE, and finally DE. And this gives us a total of 10. 10 ways to choose two letters out of these 5, and we don't care about the order. And let's say we do care about the order, then how would this change? Then that means for each of these that I've listed here, we can flip them. We'd have BA, CA, DA, EA, CB, DB, EB, DC, EC, and ED. And this would give us a total of 10, which is double the number. Yeah, we multiply by 2. And so that's basically the difference between combinations and permutations. In permutations, you order the sets that you choose, whether that be you have to multiply by 2, multiply by 3, or multiply by how many number. And sometimes it's not even the same for everything, but that's a bit more complicated. So this is fairly straightforward, but we probably don't want to be counting these by hand, especially if we have bigger sets. If we want to choose 5 letters from a set of 10, then that would take quite a long time. So we're going to introduce some, I guess, formulas that will help us. We move the screen down. Is 4 plus 3 plus 2 plus 1 a pattern? Yeah, I guess you could say so for this specific question, I guess. So let's first talk about the formula for combinations. So we can denote, if we want to choose k objects from a set of n, then we denote that as NCK. Or more often, you probably see it as n choose k. And these are basically the same thing. Is permutations the one where order matters? Yes, permutations are the one where order matters. And the formula for this n choose k, or NCK, this is going to be n factorial divided by k factorial times n minus k factorial. And we can try this out with our letters from before. So we had 5 letters, right? So n would be 5 because that's the set we're choosing from. And we want to choose 2 letters. So that would be k is equal to 2. And if we plug this into the formula, we would get 5 factorial over 2 factorial times 5 minus 2 factorial. This is just 5 factorial is 120. Oops. 120, and then we divide by 2, which is just 2 factorial. And then 5 minus 2 is 3. 3 factorial is 6. So this will give us 10, just like we had before. Someone asked, who am I? Basically, since I won't be having a TA today, also for those of you who just arrived, please send me all of your questions to the account called Send Me Questions, and then I'll be able to see your questions there. You don't understand. Which part do you not understand? Please clarify on that. And so moving on, let's talk about permutations. So permutations, we denote that as NPK, which is similar to NCK. And let's suppose we have our example from before, the letters. What we did differently from combinations to permutations is we multiplied by 2, because that was the number of ways to arrange each set of letters. So we had AB, and then it could also be BA. So for each original set, we had 1 extra. So we multiply by 2. And here we can do something similar. So let's say we have our combinations and we chose a set of k numbers. And then we have to order these k numbers now because we're dealing with permutations. So the number of ways to order k letters is k factorial. And the reason that is because the number of ways to choose the first letter is k. And then there's k minus 1 letters left. So we multiply k minus 1 for the second slot. For the third slot, there's k minus 2 letters left. And then we multiply these all the way down until there's only 2 letters and then there's 1 letter. So this is just k factorial. What is this? What are you referring to? Like, what am I going over? Because right now I'm going over combinations and permutations. Or are you talking about the account? And so because we multiply k factorial, we just take this formula up here and we'll multiply that by k factorial. And in doing that, the k factorial on the bottom will cancel. And our formula for permutations will just be left with n factorial divided by n minus k factorial. And this is our formula for permutations. And let's try this out again. So before, when dealing with our letters, we had 20 cases when we were dealing with permutations. So let's see if we get 20 using this formula. So once again, n is equal to 5, k is equal to 2, and plugging into the formula, we get 5 factorial divided by 5 minus 2 factorial, which is 3 factorial. So this is 120 over 6, which is indeed 20. So these formulas do indeed work. And I also want to know another important thing when dealing with combinations is that if you have n choose k, and this only works with combinations, not permutations. In fact, the majority of the things we'll be dealing with today are going to be related to combinations, since they're a lot more, I guess, they're more fluid, they're more popular in questions, they show up more than permutations, so we're going to be dealing with them more generally. So we have, oh yeah, what I was going to say is that n choose k, this is equivalent to n choose n minus k. And some of you may know this already, but the reason this is because if we go back to the formula, n choose, or n factorial over k factorial times n minus k factorial, if we replace the k with n minus k, then we just get n minus k factorial here. And this would be n minus k factorial. And this is just equivalent to k factorial. So again, we have our k factorial, our n minus k factorial. So this just proves that these two are interchangeable. And the reason this is useful is because, well, let's say we have a big calculation like 18 or 20 choose 18. That would be a lot of work. You'd have to 20 factorial, 2 factorial, 18 factorial, and this would cancel out, which we'll talk about later. But basically, if you want to do it faster, this is just essentially 20 choose 2. And what I was talking about canceling out is that if you look at this, if we write it out, this is basically 20 times 19 times 18 times 17 times dot 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 times 2 times 1. And then we divide it by 2 factorial, and then we also have 18 factorial. 18 times 17 times 16 times 15 times dot 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 times 2 times 1. And basically, all of these terms will cancel out, and all of these terms will cancel out. And all we're left with is 20 times 19 divided by 2. And this is 190. I guess this cancels. So namely, when dealing with combinations and permutations, the n factorial will always cancel with the n minus k factorial. And all we're going to be left with are the k biggest numbers descending from n. So that's what we had here, right? We are left with the two biggest numbers starting from 20 and 19. And on the bottom, if we're dealing with combinations, we'll have k factorial. So let's say we are dealing with 20 choose 3 instead. Then all we have to do is write the three biggest numbers starting from 20 times 19 times 18, and divide that by 3 factorial. And that would cancel. This is 3, 1140. So that's a quicker way to look at these combinations, and basically you're just skipping the step of canceling in your head to make it faster for yourself. So now let's go over some problems that deal with combinations, but not in a direct way. So a lot of the problems you're going to see dealing with combinations are going to involve bijections, in which a bijection is a one-to-one correspondence, meaning that the number of ways to count something directly corresponds to the number of ways to count something easier, if that makes sense. And if it doesn't, I'll show you an example to tell you what I mean. Okay, so, oops, that was an empty page. So let's talk about this question. This question states that we want to find the number of strictly increasing and strictly decreasing 5-digit numbers. And by strictly increasing, I mean that the digits have to be, each digit has to be greater than the last. It cannot be equal. So like in the example, 1, 2, 5, 8, 9. 2 is greater than 1, 5 is greater than 2, 8 is greater than 5, and 9 is greater than 8. But in the second example, we have 3, 4, 6, 7, 7, 9. Or actually, this is a 6-digit number. Oops. We can pretend we don't have the 3. But 7 and 7 are the same number. So it's not strictly increasing. Oops. Is my internet okay? I hope so. But yeah, there's 2 examples here, right? And so how are we going to find the number of strictly increasing and strictly decreasing 5-digit numbers? Well, in order to do that, we're going to look for a bijection. So first we have to note that the numbers must contain 5 unique digits, right? For example, 4, 6, 7, 7, 9, that didn't work because there's 1 digit repeated twice. Yeah, exactly. The numbers, you don't want them to appear more than once. So therefore, we have to choose 5 distinct numbers from 0 to 9 in order to form our number. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We want to choose 5 of these. And yeah, like someone in the chat said, if we have these 5 numbers, then there's actually only one way to order them such that they're strictly increasing. So if we choose any 5 numbers, we can say 1, 2, 4, 6, 7. This is the only way to arrange them such that they're strictly increasing. If we order them any other way with like the 4 in front, then you'd have something where 4, 6, 2, 1, 7, that wouldn't be strictly increasing. This is the only way to arrange them such that they're strictly increasing. And this is true for any subset of 5 numbers, 5 unique numbers chosen from 0 to 9. Actually, except for 0. If we have 0, then that means we're going to have to put the 0 at the front, which doesn't make it a 5-digit number. So instead, we're going to choose only from 1 through 9 for the 5-digit number, for the 5-digit increasing numbers. However, if we want to find the decreasing numbers, then instead, all we have to do is just go from 0 to 9 again, because when we're dealing with decreasing numbers, the 0 can be put at the end, and that still makes it a valid number. And if you're confused by what I mean, is that if we have the 5 numbers that we chose are 0, 2, 3, 6, 7, then this is not a valid increasing number because the 0's at the front, and that makes it a 4-digit number. However, if we want to form a decreasing number, then that'd be 7, 6, 3, 2, 0. And this is indeed a valid 5-digit decreasing number. We don't actually have to multiply by 5 factorial to each number, and the reason for that is because these numbers are already in their fixed arrangements. Basically, what that means is for each 5 numbers that we choose, there's only one way to arrange them, such that they're strictly increasing or strictly decreasing. So all we need to do is choose the 5 numbers from this subset of 9 numbers or 10 numbers, if that makes sense. So for the strictly increasing numbers, again, we said that we only wanted to deal with the numbers 1 through 9. So we just want to do 9 choose 5. And from earlier, remember that this is equivalent to 9 choose 4. And when we write this out, this is equal to 9 times 8 times 7 times 6 divided by 4 times 3 times 2. The 3 and the 2 will cancel with the 6. This will cancel with that. And we're left with 18 times 7, which is equal to 126. So this is the number of strictly increasing 5-digit numbers. And now let's talk about the number of decreasing ones. So we'll have 10 choose 5 instead. And this will be 10 times 9 times 8 times 7 times 6 divided by 5 times 4 times 3 times 2 times 1. So the 3 times 2 will cancel with the 6 again. The 5 will cancel with the 10. The 4 will cancel with the 8. So we have 18 times 14. This is equal to 252. So these are our 2 answers. And so the key to this question is seeing that all we had to do was create a bijection between the number of strictly increasing and strictly decreasing numbers and the number of ways to choose from a subset of 9 or 10. Why is it 10 times 9 all the way to 1? So that's something I was talking about earlier. You might have missed it. So when dealing with combinations, so we'll take this 9 choose 4 example. You might know it as 9 factorial times 4 factorial times 9 minus 4, which is 5 factorial, right? So you'd have 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2, all the way to 1, like what you said. But however, we have this 5 factorial here, 5 times 4 times 3 times 2. So this will just cancel with that. And it'll just leave us with the first 4 terms at the top, which is what we had here. The first 4 terms at the top. And then at the bottom, we still have the 4 factorial. And this corresponds to that. Why can't we see the people in the zoo? I don't know what you mean. Like the participants? I don't know. There might be a participant button at the bottom where you can see, but I'm not sure. Because I think my interface is slightly different from you guys. But yeah, let's move on to the next question. So this question is from the 2008 AMC 12B. And I'll give you a second to read it, but it says there's 16 parking slots in a row, and then 12 cars arrive. And each of which requires 1 parking space. And then the drivers choose these spaces at random from among the available spaces. And then this Auntie M comes along, and she has a larger car, which requires 2 adjacent spaces so that she is able to park. And then it asks us, what is the probability that these cars are arranged in a way such that she can park? Meaning that there are two adjacent spots. So I'll ask, can we use recursion for this? I don't think so. Well, I'll give you a second to think about it. Okay. So for this question, the key to doing it is that instead of assigning cars into parking spaces and then seeing which spots are empty, we're going to imagine that the 12 cars are already lined up from them. And then we want to insert the 4 remaining parking spaces around them. So basically, since we have 16 spaces and 12 cars, we have 4 empty spots, right? And the key to this problem is going to be arranging these 4 empty spots in such a way that Auntie M has a way to park her SUV. So let's go ahead and denote the cars using C, and then I'll denote an empty spot using blank, I guess. So we have 12 cars. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have the four blank spaces. And so one way to assign them would be something like this. We have 1 blank space here, 1 blank space here, 1 blank space here, and 1 blank space here. So this would be one way to arrange the cars. And if you note, here, there's no way for Auntie M to park her SUV because there's no 2 adjacent spaces. We have the 4 empty spaces, but they're all separate from each other. So there's no way for her to be able to park her SUV. We can draw a separate case. Okay, so in this case, we have 1 space here, 1 space here. We have 2 spaces here. So basically in a case like this, we have 1 spot available to park her car. Someone asked, use complementary counting. Yes, that's exactly what we're going to do actually. We're going to be counting the number of ways that she can't park her car. And the reason for this is that the number of ways she can't park her car is relatively simple to count, because you note that each of the 4 spots has to be separate from each other. And in total, there's 13 possible places to place the empty spots, right? There's here, 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 here. That's 13 available spots between the C's and around them, such that you can place an empty spot. And since we want exactly 4 of those filled, then the number of ways to fill them is just 13, choose 4. And again, this is the total number of ways that we cannot park her car. And in order to find the number of ways that she can't park her car, we just subtract this number from the total number of ways to arrange the cars. What's the total number of ways to arrange the cars? Well, there's 16 spots, 12 cars. Then that would obviously be 16 choose 12, or which is also equal to 16 choose 4. And then we want to subtract these 2. So can you use stars and bars to find the number of solutions to? Yeah, I think so. This is basically using stars and bars actually, right? Because each of the C's is like a star. Each of the parking spaces is like a bar. So yeah, you definitely could. You could also use a more direct way. why is that the number of ways not to be able to park the SUV? Okay, so the reason that 13 choose 4 is the number of ways to not park the SUV is because if we don't want the SUV parked, then that means the 4 spaces have to be separate from each other. And if we want to make sure they're separate, then we can assign them into these 13 distinct spots where there's green dashes. And if we assign them into here, then there's no way for the spots to be adjacent to each other, which means that on TM won't have the 2 adjacent spaces needed to park the SUV. Like, you can try it for yourself. No matter what ways you arrange the parking spots to fill these, to where these green dashes are, basically, there's no way for you to have 2 adjacent parking spots, since the maximum number of spots you can have per green dash is 1. And the number of ways to count that is just 13 choose 4, because we again have 13 spots and we want to choose 4 of them to put the empty parking spaces in. So let's go ahead and calculate this. So 16 choose 4, that's 16 times 15 times 14 times 13 divided by 4 times 3 times 2. Just cancels out. This is 10 times 14 times 13, which is 1820. And then 13 choose 4, that's 13 times 12 times 11 times 10. This is equal to 1105. So the total number of ways to park her car would therefore be 1820 minus 1105 is equal to 700. Wait, hold on. This is wrong. This is 715. Not the other way around. I messed up. That's 715. We have 1820 minus 715 is equal to 1105. And since the question is asking for a probability, we have 1105 divided by 1820, which is equal to 17 over 28. Is it just me, or is there a bit of lag? Yeah. My internet's not the best, so there's a bit of lag when I write. Why did I stop at 10 on the 13 choose 4? Okay, yeah, so this is something I went over earlier. Basically, if we have the 13 choose 4, we have 13 fact. Wait, my pen's not writing. What's up? Okay, there we go. We have 13 factorial divided by 4 factorial times 9 factorial, right? And we have 13 times 12 times 11 times 10 times 9 factorial divided by 4 factorial times 9 factorial. So basically the 9 factorial cancels, and we're just left with the 13, 12, 11, and 10. And then we have the 4 factorial on the bottom. How did I get the total number of arrangements? So there's 16 spaces, right? And there's 12 cars. So that's just 16 choose 12, because we want to choose 12 spots for the cars out of the 16 total. And 16 choose 12 is equal to 16 choose 4 because of the identity I went over earlier, where n choose r is equal to n choose n minus r. Oops, that's a bit messy. Hopefully you can tell what I wrote. But yeah, now we have our final answer here. So next I'm going to be going over some combinatorial identities. So the two I'm going to go over are Pascal's identity and hockey stick identity. And these are perhaps the two most useful and popular ones. So Pascal identity states that for two positive integers, n and k, yeah, hockey stick, it's a funny name. I'll show you where it comes from later, but if you don't already know. But let's focus on Pascal's for now. It basically states that with two positive integers n and k, we have n minus 1 choose k minus 1 plus n minus 1 choose k, and that will give us n choose k when we add the two. So as you can see, the pattern here is that both of these numbers, n minus 1, they're increased by 1 to be n, and then we take the larger of the two denominators and make that, or not denominators, but larger of the two numbers that we're choosing, and that also translates to the answer. And I guess I'll just show a quick example. So we have, let's say 7 choose 3 plus 7 choose 4. This is equal to 8 choose 4. Yeah, we actually are going to be proving this. My thing lagged. Oh yeah, my bad. My internet's kind of bad. We're going to be proving it in two different ways, actually. The first way is we're going to be proving it algebraically, and then the second way is going to be forming a combinatorial argument, which is basically we create like a problem in which there's two ways to count it, and they typically represent either side of the identity that we're trying to prove. So let's go ahead and prove this algebraically first. So let's expand the combinations on the right-hand side, these two. So if we expand them, we get n minus 1 factorial divided by k minus 1 factorial multiplied by, now we have n minus 1 minus k minus 1 wait, oops, the factorial is supposed to be outside. So yeah, that's the first combination. And then the second combination is n minus 1 factorial divided by k factorial times n minus 1 minus k factorial. So what do we do from here? Well, first let's go ahead and rewrite this. This is equal to just n minus k factorial, since if we expanded, the ones cancel out. But now we have two fractions basically, and they have slightly different denominators, and we're going to try and make them equal so we can add them. So in order to make the two have a common denominator, multiply the numerator and denominator of the first fraction by k factorial. So let's move the screen down a bit. In doing that, we have n minus 1 factorial times k factorial. And if we multiply the denominator by k factorial, and we combine that, or sorry, not k factorial, we just multiply it by k. If we multiply k by k minus 1 factorial, that just leaves us with k factorial. Oops. K factorial. And then we also have the n minus k factorial from earlier. Yeah, my bad. I meant to say k, not k factorial. And then for the other side, or the second fraction, we want to multiply by n minus k. So this will give us n minus 1, this is a factorial here, n minus 1 factorial times n minus k divided by k factorial. And then when we multiply n minus 1 minus k factorial by n minus k, then we just get n minus k factorial. So now we have two denominators that are the same. So now we just have to add the two. We can factor out the n minus 1 factorial. And we have k plus n minus k. and the denominator is still k factorial times n minus k factorial. And this is just equal to, since the k's cancel out, n will remultiply by the n minus 1 factorial divided by k factorial times n minus k factorial. And since we have n times n minus 1 factorial, this is just n factorial divided by k factorial times n minus k factorial. But hey, what do you know? This is the exact form for n choose k. So therefore, we've proven algebraically that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. So that's the way to do it algebraically. And the key to this was remembering that if we have k and k minus 1 factorial, if we multiply these, this just gives us k factorial. That's the key thing to remember here for this problem. Let's now try a combinatorial argument. And basically this means that we're gonna create a hypothetical scenario in which we can count in two different ways. And one way is gonna relate to the left side of the equation, and the other way is gonna represent the right side of the equation. So some identities are easier to solve algebraically, some are easier to solve with a combinatorial argument, but since the two we're gonna go over today are like pretty simple, we can solve them both ways just to demonstrate. So let's see. So let me rewrite the identity at the top of the screen. We have, hold on, I think my pen's not working. Yeah, I know it's not working. I'm trying to fix it. This is weird. Well, I guess I'll just write with my hand. Don't worry about time. I can extend this however long I want, but I have a set amount of material I want to get through today. You can. It's okay, the recording will be up. So if you ever miss anything, yeah, but we should finish on time today, don't worry. So what was I gonna, oh yeah, I was gonna rewrite the identity. So we have n choose k, n minus 1, k, oops, not n minus k, n minus 1, k minus 1, plus n minus 1, choose k. Wow, writing with your hand is tiring. But is this pen book? No, this is a OneNote. It's different from what Naveen uses. So basically, for this identity, we're gonna assign, or rather, we're gonna try and choose k people for a committee out of n total people. And that's what this left-hand side represents. we want to choose K from N. So we're going to choose these K people for a committee. And in dealing with the right side, we're going to assign one special person. And this person, it doesn't matter who it is, but we're going to do casework on whether or not this person is in the committee or not. So let's say this person is guaranteed a spot in the committee. Then that means there are K minus 1 other spots in the committee left to fill. Because there's K total, we have 1 spot filled, there's K minus 1 spots left. So we're gonna have to choose K minus 1 people. And the total number of people that are left is N minus 1, because we had N total, and then we took away the one that's guaranteed to be in the committee. So we have N minus 1 people left. So we have N minus 1 choose K minus 1. So this case is person is in committee. And he's guaranteed to be in the committee. And in the second case, we're going to deal with when this person is not in the committee. When the person is not in the committee, then we have N minus 1 people left still. Please stop spamming the chat or I'll remove you from the meeting. There's N minus 1 people left to choose from because the person, wouldn't it be the other way around? No, this is right, because if the person is in the committee, then we have K minus 1 people left to choose. K minus 1 slots for committee members left. What is a com? That's just me writing committee because I'm too lazy to write the whole thing because my hand hurts. And in the second case, if the person is not in the committee, then we still have the K committee slots left to fill. And we still have the N minus 1 people to choose from because, again, we can't have the person who's not in the committee. So that's why we have N minus 1. And the K, again, is from the K committee slots that are still open. And these two cases together, they form this case here. Because our two cases, he's either in the committee or he's either not in the committee. And there's no other case than that. We're not overcounting, we're not undercounting. And therefore, we get this relation proven. And we proved it by a combinatorial argument. So next, let's go over hockey stick identity. So this one states that it's a bit long, but for positive integers n and r with n greater than r, then we have this summation, r choose r plus 1 choose r plus r plus 2 choose r all the way to n choose r. That's equal to n plus 1 choose r plus 1. So what you'll notice is that all of these combinations, they're choosing r, and they're consecutive numbers from r to n. So you can do this with anything. So like we have 4 to 7, for example. 4, 5, 6, 7. These are 4 consecutive numbers. And we have to choose the same thing. Let's say we choose 3. 4 choose 3, 5 choose 3, 6 choose 3, 7 choose 3. And we add all these up, or summation, because I don't want to write at signs. This is equal to, so we take the greatest number, which is 7. We increase that by 1, 8. And then we take the numbers that we're choosing, 3, and then we add 1, and that's 4. And this is hockey stick. What is the sign on the left hand? That looks like an E. This is just, I just write the sum of these 4, because I don't want to put plus signs in between them, because it'll get a bit messy. It's not like technical notation. I just want to denote that we're not doing a product here. It's a summation. That's just for clarification. So the number of terms in the middle doesn't really matter. As long as we have the consecutive terms, the final answer will be 1 greater than the largest term. So the way we're going to prove this first algebraically is by using Pascal's identity, actually. And basically, we're going to be taking 2 terms at a time and collapsing them into a new term, and then taking that and the next term, collapsing them into a new term, and so forth. It's kind of like telescoping. You could call it that maybe. But the key to starting this telescoping is we write R choose R as R plus 1 choose R plus 1. The reason is that they're both equal to 1. Because n choose n for any number n is always equal to 1. So therefore, R choose R is equal to R plus 1 choose R plus 1. Am I also will? Yeah, this is the account you should send questions to because I don't have a TA today. So therefore, I can see questions. Yeah. Yeah, no, you're good. Don't worry. So let's go ahead and write this expansion out. So we have R plus 1 choose R plus 1 plus R plus 1 choose R. So these are the first two terms of the series. Yeah, send me questions is the account that you should send questions to so I can see them. I have it open on like a desktop. So by using Pascal's identity, this is equal to R plus 2 choose R plus 1. This is strictly from Pascal's identity from before. So now that we have this term, are we going to have any practice problems on the identities? So I'll have questions, practice problems in the handout, which I'll release later today for hockey stick identity. I don't think there are any on Pascal's identity because it's less of one that you directly use in problems, and it's more of something that you use to solve other bigger problems. But I will have questions on hockey stick in the handout, but we won't be going over any examples in class because since I'm proving these, they're taking like quite a bit of time. Yeah. So we have R plus 2 choose R plus 1. Handout, yeah, I'll have a handout out for this later today. R plus 2 choose R plus 1. So now we add the next term. So we have R plus 2 choose R plus 1 plus R plus 2 choose R. And again, by Pascal's identity, this is equal to R plus 3 choose R plus 1. You remember a problem of the day that uses hockey stick? Oh yeah, it was probably, I think Naveen did the problem of the days. I don't remember. I'm not really involved with that. R plus 3 choose R plus 1. Then we add this to R plus 3 choose R. This is equal to R plus 4 choose R plus 1. So as you see, this pattern will keep going on and on forever, or not forever, but until we reach n choose R plus 1 plus n choose R. And this is our final term. So therefore, what we have at the end is n plus 1 choose R plus 1. And so basically, this is the algebraic proof. We just took terms two at a time. We added them together using Pascal's identity. Then we added the next combination. Okay, Eric, I'm kicking you out. Because he was spamming my chat, so I couldn't see it. So basically, yeah, that's how we got here. We just added the terms piecewise two at a time until we got to the end. And now I'll go over the combinatorial argument. So the combinatorial argument is going to be similar to what we did for Pascal's identity, but this time we're going to be talking about cases for n minus r plus 1 people. So the reason for that is because if you look here, we have a total of n minus r plus 1 terms in the middle, that is, from here to here, n minus r plus 1 terms. So that means we're going to have to create a scenario which there's n minus r plus 1 cases. And again, the right-hand side, it's fairly simple. The right-hand side is basically you want to choose r plus 1 people from n minus 1 people. And so basically, in order to do this, we're going to assign n minus r plus 1 people specific numbers. So for these n minus r plus 1 people, we're going to assign them numbers from 1, 2, 3, all the way to n minus r plus 1. And these people are going to be special because for each case I, with I being from 1 to n minus r plus 1, this person labeled I will be on the committee, while everyone with a lower number than them will not be on the committee. So that was a lot to take in. Let me give you an example. So for case 1, I 0 to 1, person 1 is going to be on the committee, and everyone else can be on the committee because there's no one lower than them. So for case I 0 to 2, person 2 will be on the committee. I guess they'll say on off, right? But person 1 will not be on the committee because 1 is less than 2. For I 0 to 3, person 3 will be on the committee. People 1 and 2 will definitely not be on the committee. And for so on, all the way to case, I 0 to n minus r plus 1, person n minus r plus 1 will be on the committee, and then everyone else, 1, 2, ... n minus r, these people will not be on the committee. So basically, we have our distinct n minus r plus 1 cases. And the reason that we're not overcounting anything is because for each of these cases after, we're removing the possibility of the previous ones being in the committee. So for example, in case 3, 1 and 2 cannot be on the committee because we already covered the cases where they are on the committee. So for each of these terms, for each of these I terms, the person labeled I will be on the committee. So that means there's k remaining spots for the committee. And there's a total of n minus I plus 1 people to choose for the committee. So as I goes from 1 all the way to n minus r plus 1, this will give us n choose r plus n minus 1 choose r. Let me move the screen a bit. Plus n minus 2 choose r plus n minus 3 choose r, ... all the way to r plus 1 choose r, and then r choose r. So basically, this represents the left-hand side of the equation. What we had in the middle here. And then the right-hand side is just equal to n plus 1 choose r plus 1, which is the number of ways to choose the committee normally when we don't separate it by case order. And that's basically the way to prove hockey stick identity with the combinatorial argument. And yeah, that's everything I had to go over for today. There's not a lot of example questions today because I wanted to go over these 2 important identities and they're going to take a lot of time, but I'll have some practice problems in the handout, which I'll post later today. But yeah, that's everything I have. Thank you guys for coming. Yes, what is your question? Can you rejoin the Discord? That's not for me to say. I don't know. There's I don't know what's going on between you and everyone else.